Today we want to continue looking at related rates. But it's still going to be some more chain rule. The tricky part of these problems is going to be figuring out what function we're integrating, what function we're going to differentiate. And then it's just a matter of the chain rule. So we get a function, and when we take the derivative, it's going to have a variable that's not the variable in the rate of change that we want. Yesterday, we wanted to know how fast the camera angle was changing with respect to time. But the relationship we had was between x, that distance, and the camera angle. So we weren't able to write a function of time. We had to use the chain rule after we took the derivative. So the same thing is going to happen here. Let's suppose that we're inflating a spherical balloon. We're putting 2 cubic centimeters per second of air into the balloon. At what rate is the radius increasing when the radius is 3 centimeters, 6 centimeters, or 12 centimeters? So, in addition to just knowing how to do the problem, we've got to learn how to read a related rates problem. So there's a meta that sits on top of this. The way that the related rates game is played is that you're handed, there's 3 rates that are going to be involved. dy dx is equal to dy du times du dx. We're going to ask for, say, dy dx or du dx, but the function that you're given, y is a function of u. You're given kind of like the middle one as a function. That's the one that you have to take the derivative of, but then you have to use the chain rule to find out the rate with respect to x. So if we look at this problem, one of the rates is given and one of the rates will be constant. In this case, we're given a constant rate of 2 cubic centimeters per second. So this is how much the volume is changing with respect to time. So this is our given rate. We've got to give it a name. And it's how the cubic centimeters are changing per unit of time. Cubic centimeters per second. 2 cubic centimeters per second. Of what? Of what? Of air. Yeah, we're putting air into the balloon. Yeah, I didn't write the I, so it kind of looks a little bit like R. We're putting 2 cubic centimeters per second of R into the balloon. So we've got to name this rate. It's how the volume of the balloon is changing with respect to time. So this is the change in volume with respect to time. It's how the volume is changing with respect to time. Putting a constant 2 cubic centimeters of air into the balloon. We've got to name this. I'm going to use V for volume and T for time. So the name of this one will be dV dt. The next thing that we notice is that we've got this spherical balloon. So that's giving us something about a shape. Apparently, our shape is a sphere. So we list the sphere, so we think about a sphere, and we're given a change in volume with respect to time. So I'm going to write down what I know about the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. This is the volume of a sphere as a function of its radius. So now we can see some stuff, what's going on here. The volume is related to the radius. And then the question says, at what rate is the radius increasing for these various values of the radius? So the thing that we're looking for is how the radius is changing with respect to time. This is the game of related rates. You're given you're given one rate that's usually constant. You're trying to find a second rate, then you're given a function that doesn't involve the dt. Our function is a function of the radius, not of time. This is how we play the related rates game. Any questions? So we have a function, d equals 4/3 pi r cubed, and we can find the derivative of that function using our mad calculus skills. But when we take the derivative of this function, rather than just calling it v prime, since all of our derivatives have Leibniz style names, when we write the derivative of v, take the derivative of 4/3 pi r cubed and get 4 pi r squared, that's the derivative of v with respect to r. We used r as the variable. That's the exponent that we multiplied by and the exponent we reduced by 1. So that's a derivative with respect to r. So we don't just want to say v prime. We don't just want to write v prime when we write 4 pi r squared. We want to say this is the derivative of v, but we use r as the variable, so it's dv dr. Now we can use the chain rule. So we want to write this not as v prime, but with Leibniz style notation. So we've got these three rates. We've got dv dt, dv dr, and dr dt. And we can put them into our chain rule. dv dt will be equal to dv dr times dr dt. One of these is the one that we're given. One of these is one that we use our calculus skills to find. The other one is the one that we're looking for, because that's how this game has to be played. If I ask you to solve something or find something, if there's 3 things in the equation, I have to give you 2 of them. That's just how the game is played. dv dt, we know, is 2 cubic centimeters per second. dV/dr is 4 pi r squared. And dr dt is the thing that we're looking for. Notice that when we took our derivative with respect to r, that left an r sitting in the equation. And that's why I had to ask, include additional information. At what rate is the radius increasing? When the radius is 3 centimeters. So that's where we're going to put the r. Or we could just write down our dr dt is 2 over 4 pi r squared. Now we just got to plug in our different values of r. So when r is equal to 3 centimeters, four pi times 3 squared. So I guess I should have dropped out a 2. What's that going to be? 1 over 18 pi? Now, if we trust ourselves, we'll look at dr dt and just figure out what the units on that should be. R is measured in centimeters, t is measured in seconds, so this is going to be centimeters per second. If we're not sure, we could write down the units of the rates up here. dV dt was given as centimeters, cubic centimeters per second. dV dr, that's the rate of change of v with respect to r. So this is going to be centimeters cubed, that's the units of v, divided by the units of r, which are centimeters. And dr dt should be centimeters per second. So those centimeters in the middle cancel out, and both sides have cubic centimeters per second. So it all works out. So what's that? 36 twice is 72. And then we double it again. So this fits with our intuition of what's going on. We know that the volume of the balloon is increasing at a constant rate. The radius will still increase because as the volume gets bigger, the radius has to increase, but it's going to slow down. When the volume is much larger, the radius will decrease less because that same volume is spread out over more inside of a bigger balloon. So we should expect the rate at which the radius is increasing to slow down. We also notice that if we double the radius, it cuts the rate by a quarter, because it's inversely proportional to the square of the radius. So if we multiply the radius by 2, we multiply the rate by a quarter. How's everybody okay? This is why I didn't just grab my calculator and figure out what these numbers are, because now we can see that doubling the radius cuts the rate at which the radius is increasing by a fourth, as we go from 18 to 72, and then from 72 to 288. Or we could just see it, 1 over 2 pi r squared. So if I double r, that's going to divide the rate with respect to time by 4. Any questions? Comments? Easy problem. Not to give the game away, but here is the game. We're using the chain rule. In general, says dy dx is dy du times du dx. That middle one, the dy du, that's the one that you're going to find the derivative of. Then it's one of the outside ones that you'll be given, and the other one you'll be looking for. Purple. And that's the whole game. One of those you're given, one of those that you're looking for, one on the outside, and the middle one is the one that you differentiate. But it's in the wrong variable. So that's why you need the chain rule. Any questions? My favorite is when mathematicians just write these problems to fit the paradigm of one of these is given, the other one is what you're looking for, then the middle one you differentiate. So they would set up this volume problem, and instead of the air going into the balloon at a constant rate, we say like the radius is growing at a constant rate. It's like, well, that would be hard to set up because you'd have to sit there and regulate very carefully how much volume you're putting into the balloon. You know what I mean? There are some other things that we would want to consider. At this point, we're going to have to assume that the balloon is not so strong that it will actually push back against our compressed air. So think about being in a physics class. I don't know if you've taken physics yet, but in physics class, you start off and you ignore friction and you ignore air resistance. This is to simplify the problem. So when your physics instructor is like, oh, we're going to ignore air resistance and we're going to ignore friction, they're trying to make it easy on you because we have a point to make. Like I teach physics. I only raid physics for certain problems, and then I just leave the physics to itself. But when you're like, oh, well, what about air resistance and what about friction? You got to earn that. You got to show that you can deal without friction and without air resistance before stuff can go fast enough for air resistance to be a problem. You know what I mean? Like if I pick up a ball and throw it across the room, air resistance isn't going to be a big deal. I can't throw hard enough for air resistance to really be a big deal. So I could throw a ball and it would pretty much fly as a forever. I'm not throwing it really hard. Air resistance becomes a problem when you're throwing faster. Also, when you have really terrible balls, like baseballs. Baseballs are deliberately terrible so that they're designed to not fly straight. Any questions? It'd be terrible if baseballs were shaped like golf balls, which are designed more or less to fly straight. Throw a curve ball. How? Or if they were like cue balls. Although, if baseball pitchers had cue balls, hit batsmen would certainly be a little bit more exciting. Any questions? Comments? Snide remarks? The trick usually comes down to trying to find this one in the middle, the function that you're going to differentiate. So that we can look at some more related rate style problems. One of the things that we're using with the chain rule here is implicit differentiation. Or one of the things that we can use the chain rule for is implicit differentiation. Actually, I don't need it for the next example, but that's fine. That's fine. Here's when y is related to x. And we want to find dy dx, but I can't write y as a function of x. That's what's going on here with this implicit differentiation. We want to find dy dx, the derivative of y with respect to x. The complication is we can't write y as a function of x. Fortunately for our heroes, we'll just use the chain rule. So here's an example. I have this relationship between x and y. It makes a circle of radius 3 with the center at the origin. I want to know how y is changing with respect to x, but I can't write y as a function of x. I need two functions of x, so I can't write y as one function of x. We can't write y as plus or minus the square root of 9 minus x squared. We had to undo a square, and squares obliterate any negatives. So we don't know if the square came from the positive or the negative. This is one way out. If we don't have implicit differentiation, then we have to do this, but we also have to know which one we're talking about. So y is plus or minus the square root of 9 minus x squared. This is actually two halves of the circle, the top half and the bottom half. So if we happen to know that we're working with the bottom half, we'll just use that function. But if we have one way of doing something, we have no ways of doing something. Like emergency supplies. If you have one flashlight in your house, you have no flashlights in your house. It's no good having one of something. We have one way of getting at dy dx, which means we have no ways of getting at dy dx. It's not good to just have one thing. If you can't have multiple flashlights in your house, then you should have multiple flashlights in your house. I know some of you are like, oh, well, I'm so wealthy, I don't have just one house, I just have an extra house. And they each have multiple flashlights. I don't know where they are. That's what the servants are for. And I don't just have one servant, I have multiple servants. Because if you only got one servant, you have no servants. What happens when they're not there on that day? I don't know if anybody's in that situation. But anyway, we can't write y as one function of x. We have to break it into two functions of x, and then we'd have to know what part we're worried about. Fortunately, they're only different by a negative, so it's not that different. So here's what we're going to do. I want to find dy dx. I've got x squared plus y squared equals 9. We're just going to go through and every term take the derivative with respect to x. We're just going to take this x squared plus y squared equals 9. And we're going to take the derivative with respect to x of everything. So I want the derivative with respect to x of the x squared plus the derivative with respect to x of the y squared. And then on the other side, we'll have the derivative with respect to x of the 9. This might look like I'm using the distributive property. I am wholeheartedly not using the distributive property. The distributive property is what we do when we multiply over a sum. We distribute the product over a sum. I'm not multiplying by d over dx. I'm applying this operator d over dx. What's the derivative of x squared with respect to x? 2x, no problem there, just 2x. And purple. The next term is the derivative with respect to x of y squared. Now we want to write 2y, but that's not the derivative with respect to x. That's the derivative with respect to y. So we do want to write 2y. I'm going to write plus 2y, but that's the derivative with respect to y. This is the derivative with respect to y. So what do we have to multiply by to get the derivative with respect to x? dy dx, the thing that we're looking for. And I'm just going to write it as dy dx. And then over on the other side, we'll take the derivative with respect to x of 9. And how much is that? 0. The derivatives with respect to x were all purple. That's why I was able to split the derivative with respect to x of y squared into red and blue. So there we go. So this is where we used implicit differentiation because y was related to x. But when we write 2y, that's the derivative with respect to y. The chain rule says now you have to multiply the derivative of y with respect to x, and that would be a derivative with respect to x. Notice that the dy's cancel out. Not really, but close enough. Now the goal was to find dy dx. I could just solve for dy dx. I'll subtract 2x from both sides and then divide by 2y. So dy dx is equal to minus x over y. The 2's cancel. Now this is the derivative, dy dx. So this should still be the slope of the line tangent to this circle at any point x, y. The slope in the normal sense, rise over run, the change in y divided by x. So this is the slope of the line tangent to the circle. So if we go to various points around this circle, say at this point 3, 0, the tangent line is vertical, and so the slope should be undefined. And it's going to be minus x over y. 3 divided by 0 is undefined, so the slope is undefined when y is 0. At that point on the top, at this point up here, we've got the point 0, 3. The tangent is horizontal, and our slope will be minus x over y, 0. So that tracks. If we look at that point in the third quadrant at 225 degrees. Where x equals y. We have a slope also at 45 degrees, and our slope is equal to 1, negative 1. Because the x and y are the same, and then we have the negative 1 from subtracting. Questions? Yes. Because the 9 doesn't matter. We took the derivative of 9 and it ended up being 0. Now, if we replace the y down here with one of those expressions, in the first 2 points I used, it wouldn't matter. But if I look for the slope down here, I would have to make sure I use the minus square root of 9 minus x squared. The 9 would show up, but it would be canceled out once I figure out find out the x and the y's are the same. So when we plug this x into our expression, we get the same value. So it all works out. Questions? How's everybody okay? This is called implicit differentiation. It's what we do to find dy dx when we have y and x related to each other in an equation, but I can't separate them out into a function. Or it's going to be inconvenient to separate them out into a function, because I'd have to use 2 functions. Plus, if I took the derivative here, it's going to be minus 1/2 9 minus x squared times negative 2x. This was just taking x squared plus y squared equals 9 and solving for y and using the negative one because I was looking at this bottom half of the circle. Notice that the 1/2 and the 2 cancel out, leaving an x on top. The negative and the negative cancel out. So we just have an x over a square root of 9 minus x squared, which is equal to y. Or minus y. Any questions? Comment? Slide them up. How's everybody okay? All right. That's going to do it for today. I will see you all on tomorrow. Have a good day, and thanks for playing.